Resonance, also known as delocalized bonding or pi bonding. Okay, we'll look at resonance here in detail. Let's start by looking at stability of conjugated dienes. Okay, this is a diene, as I mentioned. It's got two enes, two different types. This one's conjugated. Double bonds are conjugated here. The double bonds are not conjugated. Okay, conjugation is overlap of p orbitals. Of course, you have two p orbitals here, and then two p orbitals here. We see, yes, pi bond here, but guess what? These are overlapping as well. And so all four p orbitals are overlapping. This alkene is conjugated with that alkene. Okay? Now that looks like a single bond there. That's because that line bond drawing is not fully descriptive of what's going on. Eric?
Does the final carbon also go p bond or pi bond?
No, that's four things attached. It's sp3, no p orbital. If there was a lone pair there, it would. But a signal bond is not going to do that. Over here we have pi bond and pi bond. Are those two pi bonds conjugated? Or I can say, are they connected? No, because right here there's an sp3 carbon. Okay, no p orbital. Right there. Those are two isolated alkenes. They're not said to be conjugated alkenes. Okay, which is more stable? We can look at heats of hydrogenation. If you hydrogenate these, you saturate here, you reduce here and here, and you get 1, 2, 3, 4, 5. Hydrogenation of both of these gives pentane. But this one gives off more heat. It's more exothermic. That implies that this has got more energy to begin with than that. This is not as stable. This is more stable. Why? Because it's conjugated. Okay, then you could say, well, why does that make it more stable? Well, because we have additional p orbital overlap. This is overlap of two orbitals and two orbitals, but we have this additional p orbital overlap in between. That leads to stability. Orbital overlap, typically a good thing, leads to stability. Conjugated diene more stable than non-conjugated diene. Okay, look at a couple of guys over here. This is called accumulated diene. The carbon has two double bonds. Okay, we sort of saw that a little bit earlier in the review session. Those two double bonds are not conjugated. Okay, because if you look at the structure, what's the hybridization of the central carbon? SP has two p orbitals. Okay? One p orbital is straight up in the board, overlapping with the p orbital next door, but the other p orbital is coming out this way. It's orthogonal or perpendicular to that p orbital. Since that one's coming out this way, this one's coming out this way. And so these two are like this, while the other two are like that. Two pi systems are perpendicular to each other. They're not overlapping. Because remember, for p orbitals to overlap, they have to be perpendicular. They have to be straight up and down. That is not overlapping. P orbitals have to be side-to-side overlapping. So these two pi bonds are not conjugated. It's called accumulated. Benzene is the granddaddy of all aromatics. It's a cyclic conjugated system. Fully cyclic conjugated system, that's called aromatic. You draw the p orbitals there, every carbon has a p orbital, and they're all lined up like toy soldiers. If you want to draw the ring flat, then they're all sticking out, six around, all lined up. Okay? You should make sure you understand these two structure of these. Okay, conjugated versus non-conjugated. Resonance. Well, we're looking at Roman numeral 1, neutral conjugated alkenes. Okay. And this here is indeed 1. I'm actually going to skip this. It's difficult to show resonance of this because, first off, it's easier to show resonance of a cation or an anion. We'll see why. The charge is a place for us to kind of focus in on. You don't have that focus here. Also, if you're going to deal with just a neutral molecule, it's easier to show resonance when you have a heteroatom, like an oxygen or nitrogen. Because then you can say the electrons are going to be polarized this way. Because there's no charge and there's no polarization, you're left, it's kind of like, what do I do? Let's skip it. Because I think I want to start with some easier examples, or at least examples that are more intuitive. Not that that's difficult. Okay, as we move forward down here, we do need to make comments on things called like resonance hybrids, including the true structure of our hybrid, partial charges, bond lengths, etc. Let's move down to number 2, which is resonance stabilization of cations. And let's do resonance of this cation here. Importantly, we're going to delocalize the positive charge. It's a major consequence of resonance. Okay, we got this cation. We'll start writing over here. Do we need the light on when I write over here? Tell me if I need the light on, because it's darker over here. There's 2 ways to address these topics here. One is going to be very theoretical, sort of showing the orbitals. Okay. The other is going to be very practical. Okay, what do we need to do on the board? How do we work the problem? Okay, 2 different approaches. Let's do theoretical first. Structure, orbitals. We know we have p. I'm going to redraw this over here. We know we have p orbital, overlapping. That's that pi bond there, right? It's 1 electron in each, overlapping to make pi bond. What's hybridization of the carbon over here? What's hybridization of this carbon? First off, you got to know there's 2 H's there. sp2. Okay, has a p orbital. Okay. What's in the p orbital?
Nothing.
We're the 2 H's, trivial planar, empty p orbital. Okay? And it's just a positive charge because it's missing an electron. But this empty p orbital is not just sitting there by itself, it's doing what? It's actually conjugated with the alkene pi system. It doesn't have to have an electron to interact. This is where we're actually blending a little bit of molecular orbital in here, but it does not. This empty p orbital is interacting with those. Okay? And that's essentially the structure. But we need to look at this in a different view. Let's look over here, practical. How do you stabilize a cation? Do you move electrons towards it or away?
Towards it.
Towards it.
Yeah.
Okay? What we can do here is we can take these pi electrons and move them towards it like a windshield wiper. Boom. And if I windshield wiper them over, what does that give?
You're in it.
We now have double bond there, and now we're missing a bond over here and it's plus over there. So we windshield wipered it over. Now, we only move pi electrons. Because what do? We only move like the pi bond. We didn't move the sigma bond and say, hey, there's a pi bond left. No, that's a sigma bond. A single bond is a sigma bond. The pi bond is gone. The pi bond was moved over. We only move pi electrons. And that's resonance. Anytime you only move pi electrons, you're doing resonance. You're showing a resonance structure. Thus, in turn, if you want to show resonance, you better only move pi electrons. If you start moving sigma electrons, you're not doing resonance. Now that's golden rule probably number 1 or 2 in the back. There's a list of golden rules of resonance. Okay? Now if you move a sigma bond, you're going to move an atom. You don't move atoms in resonance. Do we move any atoms? No. Only pi electrons. Okay? So, resonance structure. Now, when we draw resonance structures, we can look at them and say, which do we like better? This goes back to the beginning of the first day of organic. If I said draw a Lewis structure of this, you might have drawn this structure here. But some of you may have drawn that one. Now, we got all carbons. Resonance structures are just alternative Lewis structures. But you can say, which do you like better? On day 1, what do we like better? Ones that had the most bonds and it had like least charges. Well, it's the same thing here. Which do you like better? Or are they equal? These are identical. They both have a carbocation and they both have one alkene, both have the same number of bonds. Okay, so you cannot say that one's better than the other. The terminology we'll use is major or minor resonance structures. These are the same. Okay, so these are identical. These are identical. Everybody agree? Mm-hmm. Okay, when we do resonance, actually none of our resonance structures are actually correct. The true structure is a blend of these. Just like pink is a blend of red and white. If you wanted to make pink paint, what would you mix together? Red and white. Give you some pink. Pink is the blend. Okay? If you mix these together, what would you get? Well, you get what's called the hybrid. The resonance hybrid. You would have 3 carbons attached. Your attachment of atoms and geometry of those atoms would be the same as over here. But your distribution of pi electrons would be blended. That is, here you have pi bond between carbons on the right, and here on the left. Look at this. Between these carbons over here, you have double bond and single bond. What's the blend of a double and a single, or average?
1.5.
The average of a double and a single is 1.5. So it's like 1 and then a half. What's the average of a single and a double? 1.5. Then you can also blend your charges, or average your charges. What's the average of +1 in neutral?
Plus a half.
Plus a half plus. Now, I'm never going to quantify that. We'll either have a whole charge or what I will call it partial. So it's not a full plus, it's a half plus. We'll say partial plus. Okay? Well, on this carbon, what's the average of a plus and a neutral? Partial plus. How about this carbon? Neutral or neutral? What, if you kind of blend two neutrals together, what do you have?
Neutral.
It's neutral. Okay? This is your resonance hybrid. That's your actual true structure. Where it's this. It's all three are overlapping. And really, those two electrons are just spread out all through here. We could show the two electrons here. If you show the two electrons here, what you really have is this structure. Or you could show the electrons here, and what you really have is this structure. The electrons are really spread out through here. It's hard to show that though. What we as chemists do is we show these sort of fake structures and say, these are sort of well, they're fake. The true structure has partial bonds and partial charges. It's harder to work with. It's harder to show, but it's more the truer structure. Let's talk about bond lengths. Here we have a single bond, which is longer than a double. But here we have a double. So we call this ABC. Which bond length is longer, the AB, inner atomic distance, or the BC? Somebody said something about hybridization.
I said neither because the rest is all SP2.
It's all sp2 carbon-carbon bonds. Yeah. The bond lengths are actually the same. A bond length to AB is the same as to BC, inner atomic distance. We can see that here. If you could take a picture of this cation, you would see that over there if you just saw the electron density spread out. It would be a very symmetrical cation. The resonance that's a resonance hybrid. But what we do is instead we show these, because believe me, if we only showed this, structures would be very cumbersome looking. Instead, what we do is we show this and try to get you guys to understand that the true structure is a blend of these fake structures. But we will say which is major or minor. Here, there is no major or minor. These are identical. And thus you get a perfect blend. Okay, but look at the structures. Resonance allows us to spread this charge out. We can, by doing resonance, windshield wipering over, we say the charge has been spread to the other carbon. Of course, in the true structure, is this a full positive charge on this carbon? No, by spreading it out, it's only a partial plus on that carbon. This is a more stabilized cation than if you just had, that. That is an isolated carbocation. You cannot do any resonance. There's no p orbital next door. Okay? You can't start saying that the empty p orbital is going to interact, and thus we can start doing some of this stuff. You can't do that. Okay, let's look at this one down here. So this guy, we were able to draw one additional resonance structure. How How many could you draw down here? It's more than one. Can you draw resonance structures for the guy down here? Go ahead. What did we do? First off, how do you stabilize the plus?
Move electrons.
Move electrons towards it. Pi electrons. Pi electrons are pi bonds. It's the old windshield wiper, yeah? Show resonance structures. You can actually show 3 additional resonance structures. Okay, hopefully you have at least one. I'm going to put them up here. I can windshield wiper these over here. And that would give that cation, right? Just windshield wiper over, leaving this as cation. Then I can windshield wiper this up, okay? We're practicing drawing resonance structures, using arrows, mechanism arrows. Okay? We're not really doing a reaction mechanism, but we are moving electrons. So I'm using arrows to show movement of my electrons. The windshield wiper that up. We didn't do anything over there. All we did was windshield wiper those up, leaving that without a bond. Get that there. Now we can windshield wiper these over. By the way, this is your resonance arrow. Double-headed. This means we're showing a resonance structure. Okay? Resonance arrow. What can we do here? You can windshield wiper this back and go back over here, or you can windshield wiper this down, hinge it down. What does that give?
The original structure.
That gives back the original. Okay, that's drawn to the original, right? So here are 4 different resonance structures. This charge is really spread out onto that carbon, and this carbon. If we draw the hybrid, which is a blend of all these, single bond, double, double, double. Okay? So, is this a single or double here? We're never going to like do a 3/4 bond or a quarter. It's always just going to be partial. Here it has single bond character. Here it has double bond character. What's in between single and double?
1.5.
1.5. Okay? We're not going to say, hey, yes, if you had to say it has more double bond character here. But that also depends on, are these perfect equal contributors? But basically, it's not a single and it's not a double. It's somewhere in between. And that's what that means. It's somewhere in between. Now look at every one of your bonds. Double, 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 single, single, single. So it's not a double, it's not a single, it's somewhere in between. Basically, if you look at this, every one is somewhere in between double and single. And let's do this. This is a way that I like to sort of summarize by doing a little quantifying. We can go back and do it up there. Tell me this. How many p orbitals? This is called a pi system because you have lots of p orbitals overlapping. How many p orbitals are overlapping in this pi system?
7.
7 p orbitals conjugate. Okay, there's 6 here. If you drew them all, you would have 6 and 1, and they'd all, you could show them all standing like Tory soldiers. Okay. How many electrons are in the pi system? How many electrons in these 7 p orbitals? 6 electrons. 2, 4, 6. There's not one there. Okay. Go back up here. How many p orbitals were conjugated? Right? We had them drawn. There were 3, right? Lined up like toy soldiers. How many electrons were in that pi system? 2 pi electrons. Okay. We could say 6 pi electrons. They're pi electrons. Okay, for those that don't understand this, don't go home today before you understand it. I'll be here till 6 o'clock. All right? There's numbers right there. This is a way to just sort of, okay, let's just summarize and make sure we see what's going on. Okay. Up there, these are equal contributors. Down here, are these all equal? How can you assess resonance structure and say which one you like best?
Tertiary carbons are best.
The answer is a little bit difficult. Basically, they all have the same number of bonds, if you look at them. Down the road, we'll see some that won't have the same number of bonds. They all have just one charge. And the plus charge is on carbon in every structure. Okay? This would be difficult. But actually, this is major. And why is because the benzene ring is maintained. The classical benzene ring is maintained. That's just something we're going to have to state right now. By the way, here's our hybrid, but we didn't put in charges. Because the net, what's the charge here on this carbon? Partial plus. Where are the partial pluses? Well, you look at your resonance structures. That's where the plus falls. Okay? Now, this is like we put in 4 different colors and we're making a paint with 4 different colors. The problem is we're not putting in the same amount of each one. Which one contributes more?
The major one.
The major one. That means, here's the hybrid. Which one does the hybrid look more like if you had to say it looked like more like one of these? The major one. It's like you got a kid, and then you say, does the kid look like more like mom or dad? Well, this kid looks just like mom. Mom is the major contributor. Okay? Or maybe you got a kid that looks equal like both of them, and then you say, well, you don't have a major contributor. They contributed equally. That was more like back up here, right? Okay. Here you got a major contributor. Why? Because the benzene ring there. We'll say more. We'll see. We'll call more structures major down the road. Major versus minor. So those others would be minor. But this charge is delocalized. That charge is not sitting right there on that carbon. It's delocalized onto that carbon, that carbon, that carbon, shown by this hybrid. That's a fairly stable carbocation. It's got a name. When it's on the carbon next to the benzene ring, it's called benzylic. benzylic carbocation, very stable due to resonance delocalization. What if we had that cation? The phenyl means here, okay? This is your phenyl. What about that cation? Is it resonance stabilized? There's no p orbital here. No, it's isolated. It's not overlapping. Remember, this goes back to structure. And really, it's an empty orbital that's really playing the p orbital game. Remember the 7 and the 6? I'm just going to show this real quick. Well, the benzene has 6 all the way around, right?
Yes.
And if the ring is flat, they're actually all coming out and going back. Or if we turn the ring flat this way, then they're up and down. They're all 6 standing like toy soldiers. Then we have over here, empty one. You see, it's out there too. But all this is interacting, but it gets to interact too. And it becomes one pi system. 7 p orbitals with 6 electrons. Because it's missing an electron, that's why it's a positive charge, but the charge is delocalized through all there. Okay. So that was A, stabilization of a cation by pi bond. We can also stabilize the cation using lone pairs. And we've actually done this before. Stabilizing using a lone pair. How do you stabilize a cation?
Move electrons towards it.
Move electrons towards it. Okay. Here we have a lone pair. What's the hybridization of the oxygen?
SP3.
The oxygen is sp2, right? Anytime a lone pair is next to a p orbital, the lone pair is going to want to be in a p orbital. We learned that on day 2, right? What's the hybridization here? sp2. Carbocation is sp2. So what we have here is p orbital. Empty. We're going to make this. There's the oxygen, trigonal planar. One lone pair in the hybrid, the other lone pair in a p. Why? So we can get the p orbitals overlapping. See, there's pi bonding going on here between the lone pair and the empty p orbital. You see it? You have to just see it. But didn't we learn that anytime a lone pair is next to a p orbital, a lone pair is going to want to be in a p orbital? Okay, so that makes sense. This is empty. You should have been able to draw this a week and a half ago. Okay? All right. On the board, draw resonance structures. How do we stabilize a plus? We can take these electrons, move them in. What does that give? Yes, I'm moving them in to make pi bond, and I get this, one lone pair left. Now the plus is on oxygen. See this pi bond that I'm showing here? This overlap? Well, now I'm showing it with this resonance structure. We're stabilizing a cation by a lone pair. Electrons move in, make pi bond. Resonance arrow. All we moved is pi electrons. We moved the lone pair that's in the p orbital. We just said, hey, I'm showing it as a double bond because there's some double bond here. So it's a resonance structure. The charge is no longer on just carbon. It's also some on oxygen. What does the hybrid look like? What's the blend of a single bond between OC versus a double bond between OC? Bond and a half. What's the blend of positive carbon and neutral carbon? Blend of neutral oxygen and positive oxygen. Here's your resonance hybrid. Question, is this a perfect blend? Are these equal contributors or is one better than the other? They're not the same. Here you have charge on carbon, then you have charge on oxygen.
And the oxygen is more electronegative, right?
Oxygen is more electronegative.
So if you use
Which one do you like better?
one carbon positive.
If you like the one on the left, raise your hand.
Major one.
If you like the one on the right, raise your hand. Come on now, somebody raise your hand. Riley, I saw her raise her hand. Yeah, there you go. Yeah, you're right. This one. This one's major.
Really?
This one's minor. Why is this one major? It has more bonds. We made a pi bond. That's more bonds is better. Okay. Why did you like this one better? Because you're looking at the charge. You say charge, you would prefer to be on carbon than oxygen. Oxygen doesn't like positive charge, right? Okay. Oxygen doesn't mind a positive charge as long as it has an octet. Does that oxygen have an octet?
Yeah.
2, 4, 6, 8. Has octet. Well, guess what? That carbon has no octet. That's another reason this is good, because every atom has an octet. And it's got more bonds. Yes, the bad thing is the positives on oxygen. That's okay. If you look at golden rule number 3 or 4, which one of them on the back, it says that oxygen, even halogens, fluorine, you can even put a positive on fluorine as long as they have an octet, nitrogen. If you leave an oxygen without an octet, it'll get mad at you and it'll come hunt you down and it'll make you pay for that. Okay? Never leave an electronegative heteroatom without an octet. Unless we're going to do it and we're going to say, hey, look what we're doing here and this is what. Otherwise, never do it. But if it has an octet, it can have a positive. This is major. So which one does, so let me ask you this. Is there more positive on O or carbon in the hybrid? Well, since this is major, which one has more partial plus? The O. There's actually more positive character on the O. That's what it means. This is major. That means it's the major contributor. That means when these two got married, the kid looks more like, the kid has more charge on oxygen.
Is there any way
Okay.
to show that?
Do what?
Is there any way to show that on the hybrid? Can I get for your S?
No, usually for me, I just partial plus. You just kind of have to know, hey, there's actually more positive on the oxygen. Because I know that's a major contributor.
But we don't show the lone pair that is on the oxygen, right?
Oh, I'm sorry. Yeah, we need to show the lone pair. Yeah, I mean, it's got an isolated lone pair in a hybrid. Yeah. So, how many p orbitals here in the pi system?
One.
2 p orbitals, right?
No,
How many electrons?
One.
2 pi electrons. These two, that's it. There's none here.
2,
These electrons are not in a p orbital. If you graphed this a week and a half ago, you would have gotten sp2, right? sp2, boom, 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 p orbital left over. This is the oxygen, right? bond to carbon, and a lone pair. And then one lone pair is in a p orbital. That's the one we're dealing with. This one's in a hybrid. Okay, draw resonance of this guy. You can actually draw two resonance structures of this. Okay, we got a lone pair next door, which is in a p orbital. Because anytime a lone pair is next to a p orbital, you can take these, move them in. That would give boop, 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 boop. I'm going to draw these sigma bonds out. It's a plus charge on nitrogen. This is my A arrow going this way. Because I can also come back. Now the next one doesn't come from this. The next one actually comes from the original, where instead of moving that in, I can do what? I can actually windshield wiper over the pi bond, and I can get boom, boom, boom. Plus there. You can draw these out if you want. How many p orbitals in the pi system? How many pi electrons in the system? Okay? That is, if you drew the orbitals out, you'd have 4 orbitals. And if you put electrons in there, you'd have one in this one, one in that one. That would be empty, and there'd be 2 there. Of course, that would be an isolated view. They're really spread out all through there. We're trying to illustrate that with resonance structures. I drew these resonance structures. The charge has been delocalized. Which one's major? By the way, this is your B arrow, which gives this down here. Which one do you like best? This is major. It has more bonds. Nitrogen does have an octet, so that's okay. Nitrogen doesn't mind sharing as long as she keeps an octet. Of the other two, which is worst? It could be sort of, maybe not a good question, because it's actually primary. I was thinking it might look like a secondary. They're both primary. It's hard to distinguish. But if this was primary and that was if that was primary and this was secondary, then you would say this one would be better than that one, and that one maybe would be worse. They're both primary. I'm just going to call that one major and say the other two are minor compared to that one. So the charge actually sits more on the nitrogen. If you drew the hybrid, you really have partial bonds through here. Okay, the hybrid, boom, boom, boom. Okay, the sigma framework doesn't change, but you got pi electrons through here. You got partial plus, partial plus, partial plus, and you you could look at the compound, it would look kind of like that. You'd have electrons sort of smeared out through here. And you'd have sort of plus charge here, here, and here. The charge has been delocalized. Okay? That's stabilization of this cation by a lone pair, but also by a pi bond. Okay, let's finish up here for today. How does this affect regiochemistry, alkene reactions? We saw one of these during our look at alkene reactions, but if you take this alkene, react it with HBr, which product do you expect? Okay? Different cations, intermediates. This is going to have one cation intermediate, this is going to have the other, or another. Which product do you get? You get the product that has the more stable intermediate. You need to draw both carbocation intermediates and then look at them and say which one's more stable. Because that's the one that would form. Same thing down here. You don't do no benzene reactions here. Look, are you going to form cation on left or right? They're both secondary. Or are they? Yes, one will be secondary without resonance. One will be secondary with resonance. Which is going to be better? The one with resonance, because resonance will stabilize the charge by spreading it out. So please look at intermediates and predict the regiochemistry. Then please look ahead. Then we'll move to stabilizing the minus charge. And here's a big key thing. How do you stabilize a minus charge? Do you move electrons towards it? No, you want to take those electrons and move them away from the atom. Please look ahead. Okay, we'll hit this hard tomorrow morning. And we'll be moving on to the chemistry of dienes. Please look at that in chapter 17 or so. See some of you in lab this afternoon. Let's meet right